Hello, welcome to CSE 351 Introduction to Data Science. Today's topic is on principal component analysis and how using principal component analysis we can reduce the dimension of data. So far we studied the basics of linear algebra as well as probability and stats. Now we are going to use those topics. Basically, principal component analysis is the integration of both probability, stats, and linear algebra. So if you have not watched the previous videos, I highly recommend to watch those videos before starting off watching this video on principal component analysis. So what is the dimensionality reduction? So in field of data science we have a term called the curse of dimensionality. That means when you are collecting samples and then these samples they have high dimension, then working with these high dimensional data is problematic. We have some computational problems, and also there are some other issues with the high dimensional data, namely they have a combinatorial effect. That means if you have a vector of 10 or 100, there might be millions of numbers of combinations for the elements of these vectors. Also, these vectors usually represent multivariate distributions, and we would like to sample from those distributions. Therefore, if you have high dimensions, sampling from those distributions is extremely difficult. And also, if you want to use this data for classification, having high dimensional data is difficult in terms of the time and space complexity, and also sometimes it's less interpretable because many of these features we collected their noise. And also another issue is high dimensional data suffer from overfitting, which we'll discuss later. So I wanted to give you a motivation before we introduce the topic and how principal component analysis work. So look at these two row of images. These are images from some famous politicians. On the first row you have the original images, and then these images, basically each of them contains about 2914 pixels. So that's the resolution for these pictures. In other words, in terms of the information theory, if we need to have 2914 pieces of information in order to construct these images. So then PCA comes to play in here and say, I can generate the images with the same quality, but instead of having 2914 pieces of information, I only need 300 pieces of information to reconstruct these images. And this is the result I can present. So look at in the second row, let's see that they're almost indistinguishable from the original images. So that means we are achieving extremely high performance. So 90% of dimensionality reduction, or 90% compression for this data. So what I want you to do at the end of this lecture and be able to do is to get a data set it could be an image, voice, any sort of data sets, and you try to see if you can reduce the dimension of this space and then have a more compact, less noisy representation for your raw data. Before we talk about principal component analysis, or PCA, let's talk about linear transformation using matrix multiplication. So in many today's applications, apps, you will see lots of videos, images, and these images are rotated, scaled. If you wonder what is the underlying process to do this all image scaling, rotation, the process is simple. It's basically a matrix multiplication. So if I have an image and then if you multiply this image by a particular redesigned for a purpose matrix, then you will be able to do the desired transformation on that image. So I'll give you an example in here. So in here we have 4 points in this space. So this is a Cartesian plane, two-dimensional data. That means each sample has 2 attributes, x and y in here. So we have 4 points. This is the first point, second, third, and fourth point, right? So that's usually, in here it's a square. So I wanted to, and then this matrix basically is our data. It's data. This matrix is our data. I wanted to transform these vectors. So we have, in here I have 4 vectors. So this is vector 1, vector 2, vector 3, and vector 4. I wanted to transfer all these vectors such that A will be transformed to A prime, B transform in here, and then C transform in here, and D transform to D prime. So let's say I managed to design a matrix that do the required transformation. So when I multiply this matrix data by T, so T denotes the transformation matrix, then I get the new coordinate for transformed data. So as you see, this square is now stretched and also a little bit rotated using this matrix. So we can design different transformation matrices for different purposes and apply them on the data. So I can also write down this equation as follows. So this is T times V, where V is a vector, right? So this is a vector. That means for each data point, I multiply each data point by T. But in order to simplify that, if you stack all these vectors from these data sets, that would be another matrix, and this process is a simple matrix multiplication. So you can convince yourself that if you multiply each individual vectors by T and then stack them, you get this result. So basically in here I have T V1, in here I have T V2, T V3, and T V4, where these are vectors. So basically there are 2 main operations when we are multiplying our data by a matrix are taking place. The first one is called scaling, and the second one is rotating. So you can basically decompose a transformation, a matrix transformation, and show this is basically a cascade of 2 sub-transformation. One is scaling, another one is rotating. So when you wanted to scale some data, so let's say I give you an example, and instead of our data I consider a vector. So let's say we have vector V from the 2D data, and this is 5 and this is The first dimension is 5, the second dimension is 2. I wanted to scale the element of this vector. So I wanted to multiply the first coordinate by 2, the second coordinate by 5. So at the end I wanted to find a transformation. When I multiply this transformation to v, I'll get another vector, let's say y, and then so y coordinate is 5 times 3, and then 2 times 4. So what is the matrix T looks like for this scaling? So a little bit just thought about that shows that T for scaling is a diagonal matrix when we have 3, 0, 0, and 4. So as you see, for scaling, we only need to have a diagonal matrix whose main diagonal elements determines the scaling for each individual component of the vector. So in here, if I multiply this one by 5 and 2, so you see that would be also 5 times 3 and then 2 times 4. So we only in here putting the scaling factors on diagonal matrix. For rotating a vector or an image, so an image is basically a stack of vectors which can be represented as a matrix, and each column of that matrix basically is a point, a sample from this our data sets, or each coordinate of our data sets. So rotating is for two-dimensional data, we can show that the rotation has this form of matrix like a cosine of theta, sine of theta, and then in here we have cosine of theta minus sine of theta. So that's how we basically do the transformation, the rotation. So the rotation is taking place by a matrix. In here, theta will basically determine the angle of rotation, the angle of rotation. So sorry, I think I made a mistake in here. I should correct myself about this matrix. So this is minus sine, and this one is sine of theta, and this one is cosine of theta. So that's the that's the rotation matrix for two-dimensional data, and theta is the angle, the rotation around origin. For instance, if I have a vector and I wanted to, let's say this is my vector. If I wanted to rotate that vector at 30 degrees to get another vector, then this is theta, and here is, let's say, 30 degrees, minus 30 degrees. Then I need to multiply this vector with the dimension x and y, by, so this is our vector, x and y. Then I need to multiply x and y by t. So this is cosine 30 degrees, sine of 30 degrees, minus sine of 30 degrees, cosine of 30 degrees, then multiply by x and y. So that the result would be new vector. So this is two main operations for matrix transformation. Okay, so now we would like to see how we can transform the data drawn from a distribution. So the idea is like this. So if I have, so this data, this scatter plot I showed in here are 5,000 samples drawn from a normal distribution with the zero mean and unit variance. So this is a normal distribution, so or a Gaussian distribution. This one is a normal or Gaussian distribution with mean 0 and covariance matrix of identity. So the covariance matrix for this one is identity. So you can convince yourself why the formula looks like this, because we previously showed the multivariate normal distribution, in particular for two-dimensional data. So in here, x is a 2D vector. So if you wanted to generate these samples, you can refer to the notebook files, and then we have a piece of code in there. I generate this data. You can use this very handy function from the random library called multivariate normal, where in here you pass the mean vector, covariance matrix, and then number of samples you wanted to draw from this distribution, and then X would be a matrix whose columns are samples drawn from this distribution. In here I pass max, that means the mu x is mu is 0, 0, and then covariance matrix, which usually we use with capital Greek letter sigma, is equal to 1, 0, 0, 1. So what does it mean? That means the variance for each dimension is 1, and there is no correlation, or there is no interaction between x and y. So x and y are uncorrelated. That means the changing x direction doesn't necessarily change anything in y direction. So this is the data I have generated from a normal distribution with 0 mean and identity covariance matrix. So we know that this is an identity covariance matrix. So now let's say someone has done a transformation on this data drawn from this standard two-dimensional normal distribution, and we have this new scatter plot which obtained by transforming the x data to y data. So this is like x data, y data. So we transform the x to y by matrix A, and then we have these data sets which are now stretched toward this direction, this like a 45 degrees direction. So we would like to see what the transformation matrix looks like. So are we able to obtain that transformation only having access to this data? So only thing we observe is y. Now we wanted to find a. So the answer is yes, and then that's basically the basic idea behind the principal component analysis, which I'll describe shortly. So first of all, we wanted to see if the probability distribution of this standard bivariate normal distribution look like this, and then if we multiply this data from this distribution by A, what is the probability distribution for y? Y still is a two-dimensional vector drawn from a new distribution, but this distribution has a different covariance matrix. So it is proven, or you can easily verify, the probability distribution of vectors y looks like this. So now what's the difference is the mean is still zero. Mean is still zero, but we have the covariance matrix this time is not an identity matrix. So so in here sigma is a covariance matrix. So the covariance matrix is A times A transpose. Note that we still don't know what is A. Okay, if you know A, then you're done. So all we know that this data has this covariance matrix. So we have data Y, and we already show showed that if you have some samples, how to compute the sample covariance. So we can easily compute the sigma, which represent the covariance matrix. So this one is basically sigma is sample covariance. Sample covariance. Okay, so we have covariance matrix for this new transform data, and we also know that this matrix is equal to A times A transpose, where A is the linear transformation, but we still don't know what is A. But a little bit of thought tells us, okay, is there any way I can decompose or factorize the covariance matrix to two matrices, which second one is a transpose of the first one, then that matrix is the A which I'm looking for. So is there any way to do that? The answer is yes. The answer is yes. If we have the covariance, we can decompose it. Luckily, there's a very well-known and standard method, which is called the singular value decomposition of a matrix. So that means for now, for the rest of this discussion, we assume that the matrix is a symmetric matrix. So we already know that a covariance matrix is a symmetric matrix. That's one of the property of covariance matrix. So a covariance matrix or a symmetric matrix, using a technique called singular value decomposition, can be decomposed to product of the three matrices, namely V det and V transpose, where basically the last matrix is transpose of the first one. So these matrices, they have some properties. So so basically we need two matrices, V and D. V is an orthogonal matrix. We know that the orthogonal matrix is a matrix, so if V basically is a matrix of these vectors, let's say if dimension is n, if a matrix is orthogonal, that means the inner product of each pair of these vectors is 0. So that means Vi, if this is a vector, and Vj, the inner product is 0. That means these two vectors are orthogonal. How to investigate? By using the dot product, which we discussed previously. And then D is a diagonal matrix. So when D and V, they have two different tasks. The V matrix is basically responsible for rotating data, and D is responsible for scaling the data. So we already talked about what is rotation and what is the scaling of our data. Also, from another perspective, the columns of V, which obtain after these singular value decompositions, are eigenvector of sigma or covariance matrix. And the elements on the main diagonal of the diagonal matrix D are eigenvalues. So what is eigenvector and eigenvalues? So basically eigenvector and eigenvalues are some vectors which are orthogonal and also independent, and basically they represent the new direction in our data where we have the most variance of data. And also another way of looking at eigenvector. So if you multiply an eigenvector by a covariance matrix, by the matrix from which the eigenvector is extracted, this transformation basically only scale the eigenvectors. So if V1 is an eigenvector, so if I multiply sigma by V1, then the results would be V1. So that's the property of an eigenvector, but a scaled version. What is the scale? This multiplied by D1. What is D1? D1 is eigenvalues. So eigenvalue. So in other words, that the eigenvectors are the features in the space of our matrix where under the transformation of that matrix only stretch or squeezed by the eigenvalues. So that's the way we define the eigenvalue, eigenvectors. So eigenvalue values determine if a vector, how much an eigenvector is stretched or squeezed. So a big eigenvalue basically causes the eigenvector scaled, stretched, and a small one causes the eigenvector squeeze. To basically shrink or expand the eigenvectors. So this is another view of eigenvectors. So I have more explanation about eigenvectors and eigenvalues in the Jupyter Notebook file. So please also download those lecture notes and try to run some codes and visualize the results. So anyway, I don't want to just deviate from our main discussion. The discussion was as follows. So we wanted to find a transformation when we have some data, and we wanted to see under which transformation this data from standard normal has been transformed to new data. So we multiply this data by matrix A, so we don't have this matrix, but we have our new data. We compute the covariance matrix, and then we show that the covariance matrix is the product of the transformation matrix by its transpose. So now we show that we can decompose the covariance matrix to the product of the three matrices, two of which are basically identical. One of these vectors responsible for rotation, another one is for scaling. So anyway, so far we showed that the covariance matrix is equal V times D times V transpose. But this is not exactly what we are looking for. We wanted to look for A times A transpose. So then the next step is, can I build out of the product of the three matrices, two matrices, which one of them is a transpose of the others? The answer is simple, thanks to the property of matrices, we can simply, we have the covariance matrix, we decompose it to 3 matrices, and then I can, because D is a diagonal matrix, I can easily decompose it to 2 matrices. I take the square of each matrix D and then show that the covariance matrix can be rewritten as V times D square root of D. So square root of D means that because this is a diagonal matrix, all elements on the main diagonal, we take the square root of those elements. And then V times D squared transpose. So that looks what I'm looking for. So if I call this one A, then this one is A transpose. Done. So I showed that the covariance matrix can be written as the A times A transpose, where A is V times D squared. So then I have found a transformation. So now how we can find a transformation? These are 3 steps. So from the given data, first we compute the covariance matrix, and then we apply the singular value decomposition on covariance matrix to obtain the eigenvector matrix and eigenvalue matrix, and then we multiply the eigenvector matrix by the square root of the eigenvalue. Then we have found the transformation. So basically, if you have matrix X in this step I compute the covariance, sample covariance matrix, and then decompose it to V times D V transpose, and then the next step would be just finding A as V times D squared. Then done. I found. So that means now if I have some normally distributed data, I can find the transform from which this data has been transformed from a standard normal distribution to these data sets. So this is basically the basics behind the principal component analysis. So far you should know what is a matrix transformation looks like, and then how we can find a transformation by singular value decomposition. Then next I'm going to talk about how using this concept we can do the principal component analysis. So now we are ready to talk about principal component analysis. So before we introduce a singular value decomposition, and then singular value decomposition basically gives us the eigenvectors and eigenvalues of a covariance matrix. We know that when you do the SVD, the singular values are ranked. The first singular value has the highest eigenvalue. So, and second one is the second, and third one, and so on and so forth. Let's say if I get the V as V1, V2, V3. So these are vectors. So this is eigenvectors. And if you get the D as D1, D2, D3, and this all element 0 because it's a diagonal matrix, we always note that D1 is greater than D2, and this D2 is greater than D3. It's all order. And also V1 is more important than V2, and V2 is more important than V3. So V1 is basically is eigenvector or a principal axis in the direction that the data have most variance. So what does it mean? So if you look at these figures, so if this is scatter plot, so this is scatter plot looks like this. So we see that in this direction, data has more variability. That means the variance within the direction is the largest one. So singular value decomposition decomposes the matrix to eigenvectors and gives us the principal components or eigenvectors which are ranked, and the first one is in direction of the most variability of our data. So for these two-dimensional data, because we have 2D, we have only two principal components, and then these are the two principal. The first principal component is in this direction, and second principal component is in this direction. So what basically we do, instead of considering the data in Cartesian plane now, we introduce another principal components or another way of looking at data by transforming the origin to the point that we have two orthogonal vectors, and these two orthogonal vectors now play the role of x and y axis. But why this is beneficial to change the coordinate, then when you transform data to this new coordinate, then when you project the data to the principal components, then you can compress the data, because these data in some coordinates, they are really they have less value, so we can ignore them. So now we show how to perform the principal component analysis in order to reduce the dimension. So let's assume we are given a matrix. So this matrix X, where we have n samples. So the samples, we have n samples, where we have p attributes. But the first question we need to ask, and I found that many students they have problem with, is when we wanted to apply the principal components, what do we need to compress? Do we need to compress the feature space? Do we need to compress the sample space? So it should be clear which dimension you wanted to compress. Usually when we have samples, you wanted to reduce the feature space dimension. So that's the question. But some cases you also wanted to reduce the dimension of sample space. What we then do from this data set, we compute the covariance matrix. When you compute the covariance matrix, now we can find the eigenvectors and eigenvalues, and then these eigenvectors and eigenvalues give us the directions where the data have most variability, and then because the eigenvectors are ranked according to the eigenvalues, so we observe that for some eigenvectors on the highest end of this rank, the eigenvalues are very small, so we can ignore those eigenvectors. That means if you project the data to new space, then you will introduce a little bit of noise, but the accuracy won't be compromised that much. So I'll talk about this in more detail. So then how we do the principal component analysis. Let's say you have a data matrix X whose dimension is n by p. As I said, n is number of samples and p is number of variables or features. We also assume throughout this discussion that the data is already centered. So what does it mean? That means for each column, we compute the mean and then subtract the elements in each column. We subtract the mean from element of each column. We already talked about this, and you had some homeworks. And then we compute the sample covariance matrix. After you compute the sample covariance matrix, you do the singular value decomposition. So now we have the eigenvectors and eigenvalues. So after you have eigenvectors and eigenvalues, so you project the data into the eigenvector space. So what does it mean? That's basically a simple matrix multiplication. So if you obtain the eigenvectors, you multiply the eigenvectors by the data. So this way you project your data to a new space with a new principal axis. So after you project them, these are now called the principal components or principal scores. So it's very similar to the Cartesian plane. We say the x vector x has dimension of 2 and 1, right? Now, a new coordinate, the vectors have different values. So the principal components shows these scores. So the process is simple. We have the data, we compute the covariance matrix, we compute the singular value decomposition, we obtain the eigenvectors, and then we multiply our data by eigenvectors, and then these are the principal components. So if we wanted to see how this matrix look like, this matrix after you multiply them, and this matrix is an n by p matrix. So the dimension doesn't change because V is a P by P matrix. So now the jth principal component is basically jth column. So this one, we have a new matrix. In this new matrix, the jth column in this is the new feature vector, if you wish, or new coordinate. I mean, know also that these coordinates are sorted according to their importance. And what is the definition of importance is that they ranked according to how much they explain the variability of data. And if you wanted to see how a sample now looks like in the principal component space, you just select one row. So one row now is a vector with dimension of p, but now the value of these new features are features that after projecting the data to the new feature space or new principal components. So then you're asked, okay, I had a matrix of dimension of n by p. After multiplying this one x by v, I get a matrix a dimension of n by p. So how am I supposed to reduce the dimension? So if you want to reduce the dimension, so we can choose only k principal components. So we have a matrix whose columns are principal components. Then we can choose k number of principal component rather than p, which was the original dimension. Then these new matrix whose dimension is n by k is the reduced dimensioned data or compressed data set. So for each sample, instead of we represent each sample by p features, now we use k features, right? So that's the compression. The next question we would like to answer is how we are going to choose the value for k. How many principal components we are going to choose. So that's also a very crucial question. What we basically do, we plot the the eigenvalues. We plot or cumulative distribution, cumulative sum of the eigenvalues. And then that plot shows the amount of variability which is explained up to k principal components. So I'll talk about this shortly. So as I said, in order to reduce the dimensionality, so we choose p principal components, and that P principal component gives us a new matrix whose dimension is n by k, and this is the new data or compressed data. How to reconstruct from this reduced matrix? It's very simple. You basically multiply back the kth principal components to the transformed matrix, and then we basically create the original matrix. So this is how we reconstruct the image. We know that this image now has the same dimension as n by, so this has n by p, but in lower rank space. So then we answer this question choosing the number of components. As I said, we examine the cumulative explained variance ratio as a function of number of components. So how to read this graph? So this graph means on x-axis I have the number of components, and on y I have cumulative explained variance, right? So if I include all principal components, then I have the 100% of the variability or explained variance is explained by this data. But this graph shows if I include the first principal component, that principal component only explains 10% variability in data. If I include 10 principal components, they will explain 70% of variability. Okay? If I include, let's say, 50 principal components, they will almost explain 90%. So depending on our application, we can choose how much cumulative explained variance we wanted to have for our data. For instance, if you have some image applications, if you lose a little bit of resolution, your eyes might not perceive it. So if I just choose the 50 principal component for I get the 90% of variability, and then we will see that 10% basically was some noise in our data, which principal component analysis helps us to remove. So that not only give us a very compression rate, and also give us some quality if those 10% variability is coming from noise. And also we can do the same for, let's say, speech signals, where some of our frequency are very high. If we cut them, our ear is not able to hear that. So this is how we choose the proper number of principal components. So let's see how we do the principal component analysis in Python. Here I have an example in scikit-learn. Again, as I mentioned before, you can go and download the Jupyter Notebook slides and run this example, change the value, or plot the results in order to understand how we can use the principal component analysis to reduce the dimensionality. So this is the main function we are using is called PCA. So the function we are using is PCA from the decomposition library from scikit-learn. In here, I have just created a very simple matrix. This matrix is 1, 2, 3, 4, 5, 6, 6 by 2. So I have 6 samples. Each sample is drawn. It has a dimension of 2 or 2 features. Then basically what we do, we first create an object which is called the principal component, and then we choose the number of components in here. For this example, we know that the maximum number of principal components is the minimum of the number of rows or columns. So in here, because 6 and 2, the minimum is 2, the maximum number of principal component is 2. So I set the number of components to 2, and then that basically create an object. Now I will fit the data to this object. So in here, basically, I create a function, and now I give an input, and then now the object PCA will do the principal component analysis. And this object has some methods and input and output. You can see them in Jupyter Notebook files, and then you can also plot the principal components, and also you can plot the percentage of the explained variance by each principal component, and then you can choose how many principal component you wanted to have for this data, for instance. So this is the same example. If you wanted to, this is very important function. So if, let's say we have some data, we call it digit data, and then we fit a principal component. In here, I didn't specify the number of components. Automatically will set to the minimum number of row or columns. Then this object now has some methods and input and output. If I wanted to plot the cumulative sum of the explained variance, so then from this object I call this method one of the attributes of this method, and then I plot the cumulative sum, and this gives us a very nice cumulative sum of the explained variance. So then by visually inspecting this graph, I can choose how many principal components I can choose to lose some information but reduce the dimension. I will highly recommend you go to the Jupyter Notebook slides and run those code to understand how to implement and how to handle a PCA analysis. Here is another example for the dimensionality reduction. This is the first slide I showed you, that we have around 1348 images from different people, like from 1, 2, 3, 4, from I think 12 politicians, and these are the images. And then we wanted to see if we can apply the principal component analysis to compress these images, and then to reconstruct them, and then see how much the quality of the reconstructed image is different from the original one. So this part basically load the data. These are some standard library in scikit-learn, and we have 1,348 images. Each image is 62 by 47 pixels. And this is one example, plotting one example of this case. If you apply the principal component analysis on these data sets, the cumulative sum looks like, cumulative explained variance looks like this. So initially, as you see, for each image we have 62 by 47 pixels, which is something close to 1245 pixels, sorry, 12,000, sorry, I computed this one in the first slide. What was that number? The number was 2,914 pixels. 2,914 pixels. So and here we have 2,945 pixels, right? So this is the feature space dimension for each sample. So after doing principal component and then plotting the number of components, here we only show 140 components. We see that if you choose only 140, we get accuracy close to 900. So instead of using 2,945 principal components, we will do the reconstruction by having 300 principal components. So in here, I do the PCA only on 300, and I choose only 300 first principal components, and then I fit the data. So, and then using these two functions, we do the reconstruction. As you see, this is a reconstructed image by only having 300 principal components. So the amount of reduction we have now for each image, we have 300, what do you call it, that's pixel, or not pixel, but because they are mapping of pixels in another space, let's call them 300 pieces of information. But originally we had 2,945. So if you divide these two numbers, you get a compression rate of 90% by doing the principal component analysis. And many of image processing techniques, they use principal component analysis in order to reduce the dimension. So you can run this example in Jupyter Notebook files uploaded on Blackboard, and then change the value for the number of principal components and then see the quality. I would recommend you to choose